Hello viewers, welcome back to my YouTube channel. In today's video, we shall be talking about a continuous random variable, and of course we shall be proving the mean and variance of a continuous probability distribution. And however, uniform distribution is a continuous random variable. And of course, this uniform distribution can also be expressed as a rectangular distribution. So, a continuous random variable is said to be uniformly distributed if its probability density function can be expressed as one over b minus a, where a is the minimum and b is the maximum. And of course, we have 0 elsewhere. So we shall be proving the means and variance of this distribution. However, the mean and variance of this distribution can be proved using two methods. We have moment generating function approach and normal integration method. So in today's video, we shall prove this distribution using both moment generating function approach and normal integration method. So let's have it. So let's use normal integration method to prove the mean and variance of this distribution. Of course, we know that the mean f of x is equals to integral of minus infinity to plus infinity x f of x dx, where 1 over b minus a is the f of x. So we have integral of minus integral of a to b, because a is the minimum and b is the maximum, x f of x dx. So we have integral of a to b, x1 over b minus a dx. Of course, the 1 over b minus a that happens to be uniform distribution is the f of x. So the next thing to do is to bring out 1 over b minus a out of the integral sign. So we have 1 over b minus a, integral of a to b x dx. So in here, we have 1 over b minus a. If we integrate x with respect to x, we have x squared over 2, where we have a to b. And in here, we have what? We need to put the value of our range into the value of x. So we have 1 over b minus a. Of course, the b is the maximum and a is the minimum. So we have b squared minus a squared over 2. So we have 1 over b minus a into bracket b squared minus a squared over 2. But don't forget that we can also rewrite b squared minus a squared in this form. This is this into bracket b minus a, b plus a over 2. So this cancels this. We are left with what? B plus a over 2, meaning the mean of the uniform distribution is b plus a over 2. So let's get the variance. To get the variance, we know that var(x), which happens to be the variance, is equals to expected value of x squared minus expected value of x all squared. Already we've gotten this to be this. Now we need to get this. So we have the special value of x squared is equals to integral of minus infinity to plus infinity s squared f of x dx, where our f of x is 1 over b minus a. Of course, is the distribution, is the PDF of uniform distribution. So we have integral of a to b, because our a is the minimum and b is the maximum. S squared f of x is 1 over b minus a dx. We repeat the same process. We bring out 1 over b minus a out of the integral. We have 1 over b minus a, integral of a to b, x squared dx. Now the next thing to do is to integrate this x with respect to x. We have 1 over b minus a x. If we integrate x squared, we have x raised to power 3 over 3. Now we have 1 over b minus a x raised to power 3 over 3. Don't forget our range that we have a to b. Now we need to put the value of our range into the x. So we have 1 over b minus a, b cube minus a cube over 3. Now we can also rewrite this b cube minus a cube as b minus a into bracket b squared minus b squared, using the moment generating function approach to prove the mean and variance of this distribution. And to get the mean of this distribution using the moment generating function approach, we have theta x is equals to exponential to the power of x is equals to integral of minus infinity to plus infinity exponential theta x f of x dx. Now, to get the mean of this distribution, we have mx theta is equals to exponential theta x is equals to integral of minus infinity to plus infinity exponential theta x f of x dx. Now, to get the mean, we have integral. We already know that this distribution range from a to b, where we have a to b exponential theta x f of x is the PDF to be 1 over b minus a dx. What we need to do here is to bring out this. We have 1 over b minus a integral of exponential theta x a b dx. Now we need to integrate the exponential theta x. Now we have 1 over b minus a. If we integrate exponential theta x, we have exponential theta x over theta. It ranges from a to b. And of course, we have 1 over b minus a exponential theta x over theta, which ranges from a to b. Now we can bring out this theta to multiply this. We have 1 over theta b minus a and we are left with what? Theta x. Now we need to put the range into, we need to put our range into the x. So we have 1 over theta b minus a exponential theta, the highest, minus the lowest, exponential theta a. Yeah, this is what we get. Now, for us to proceed further, we need to use the idea of Maclaurin's series. Recall that the Maclaurin series of exponential theta or exponential x is equals to 1 plus x plus yes, this is the Maclaurin series of exponential x. So Maclaurin series of exponential theta b will be given as 1 plus and of course the Maclaurin series of exponential theta a will be given as 1 plus theta a plus Now, don't forget that we are interested in exponential theta b minus exponential theta a. So we've gotten the Maclaurin series of exponential theta b and exponential theta a. Now, to get the Maclaurin series of exponential theta b minus exponential theta a will be given as, so this minus this. Of course, this is this minus this, which is this. So this minus this will give us the Maclaurin series of this expression. So we have 1 minus 1, which will give us, 1 minus 1, which will give us 0. And here we have this and this. And if you look at it, what is common between this expression and this expression is the theta. So we can bring out the theta out to be what? B minus a. Because we have exponential theta b minus exponential theta a. So this minus this plus theta squared is also common. Theta squared into brackets b squared minus a squared over 2 factorial plus theta cube. Theta cube is common in between into brackets b cube minus b minus a cube over 3 factorial all till infinity. That is what we get. So this expression, this expression is the same thing as what we have here. So we now go back to where we stop, which is what? 1 over theta into brackets b minus a. This is the same thing as this. Now we put this as theta into brackets b minus a plus theta squared b squared minus a squared over 2 factorial plus theta cube b cube minus a cube over 3 factorial. Of course, we can even still proceed and have theta 4 into brackets b4 minus a4 over 4 factorial all till infinity. So this is what we have. Now what is common between this expression is theta. We can bring out theta. So we have 1 over theta into bracket b minus a. If we bring out theta, we are left with what? Theta into bracket b minus a plus, remember we are bringing out theta from all the expression. We have theta into bracket b squared minus a squared over 2 factorial plus theta squared into bracket b cube minus a cube over 3 factorial plus theta cube into bracket b raised to power 4 minus a raised to power 4 over 4 factorial plus to infinity. So this theta can cancel out this. Now we are left with 1 over b minus a plus theta into bracket b squared minus a squared over 2 factorial plus theta squared b cube minus a cube over 3 factorial, all till infinity. Now, where all till infinity? Now, let theta equals 0. Meaning, anywhere we see theta, we put 0. Logically, everything here becomes 0. We are left with what? No. Don't they go? Okay. So, haven't us brought out the theta? Of course, this theta cancel this. Now we are left with this expression. Now, this theta cancel this. This theta cancel this theta. Now we are left with what? 1. We need to differentiate this expression with the respect to theta. So we have 1 over b minus a. If you differentiate b minus a with respect to theta, it gives us what? 0. Because b minus a is not having any theta to differentiate with. Plus, if you differentiate theta multiplied by b squared minus a squared over 2 factorial, of course, we will be given what? B squared minus a squared over 2 factorial. Plus, if you differentiate this, we have 2 theta into bracket b cube minus a cube over 3 factorial. Plus, if you differentiate this, we have 3 theta squared into bracket b 4 minus a power 4 over 4 factorial, all till infinity. Now, what we need to do next is let theta equals 0. Meaning, anywhere we see theta here, we put 0. Mathematically, this expression becomes 0. This expression becomes 0. We are left with 1 over b minus a plus 1 over b minus a multiplied by 0 plus this, because everything here becomes 0. So we are left with only this part. So here we have 1 over b minus a. This one is gone. Multiplied by b squared minus a squared over 2 factorial. Now, we can express this as what? As 1 over, we have 1 over b minus a, b squared minus a squared over 2 factorial is 2 times 1, which is equals to what? 1 over b minus a into bracket b squared minus a squared over 2. Now, we are left with what? 1 over b minus a. We can write this b squared minus a squared as what? As b minus a, b plus a over 2. This goes with this. We are left with what? 1 multiplied by b plus a. I have b plus a over 2. Therefore, the mean of the uniform distribution using moment generating function approach is b plus a over 2, which is mx theta. Now, to get the variance of the uniform distribution using this approach, we have of course the var(x) is equals to m all squared. So this is the var(x). Now, logically, we've gotten this, which is this. Now we need to get m prime prime x theta, that is the second moment. We need to get the second moment. This is the first moment, this is the second moment, and the mean is the first moment. So to get the second moment, which is what? Which is this. Now, to get the first moment, we need to get the second derivative of what we've gotten here. We need to come back here and get the second derivative, of course, the second differentiation. Now, if we differentiate this, we have what we have there is 1 over b minus a into brackets, I mean this, a squared over 2 factorial plus 2 theta into brackets b cube minus a cube over 3 factorial plus 3 theta, I mean this. We need to differentiate this again, squared into brackets b raised to the power 4 minus a raised to the power 4 over 4 factorial plus all till infinity. Now we need to differentiate this to get our second moment. Now we have 1 over b minus a into bracket of, if you differentiate this, this becomes 0 because b squared minus a squared over 2 factorial is not having any theta. So logically everything here becomes 0. Now if you differentiate this, we are left with what? If I differentiate 2 theta, I'm left with what? I'm left with 2 into brackets b cube minus a cube over 3 factorial plus, if I differentiate this, I have 6 theta into brackets b raised to the power 4 minus a raised to the power 4 over 4 factorial plus infinity. Now this is what we get. This is the second derivative of this. So what we need to do next is let theta equals 0, meaning anywhere we see theta in the second derivative, we put 0. Now if you look at this expression, the only aspect we have theta is this, meaning everything here becomes what? Everything here becomes 0, because if I put theta here, everything here becomes 0. We are left with what? 1 over b minus a into bracket of 2b cube minus a cube over 3 factorial. Now I have 1 over b minus a into bracket of 2b cubed minus a cubed over what? Over 3 factorial. And 3 factorial is 6. 3 times 2 times 1. That will give us 6. So 2 here 1, 2 here 3. So we are left with what? 1 over b minus a into bracket of b cubed minus a cubed over 3. Now, we can rewrite this expression as what? As 1 over b minus a into bracket of b minus a, b squared minus plus a b plus a squared all over 3. So this goes with this. We are left with b squared plus ab plus a squared over 3. This is the second moment of the origin. Now, because we've gotten this to be this, this to be this. Now, of course, you just need to put substitute all these things into the variance and get the value of our variance. So var x is equals to minus squared so we have var x is equals to this, which is this, b squared plus ab plus a squared over 3 minus this, which is this, b plus a, and this, which is this, which is b plus a over 2. But don't forget that it's in squared, so we need to square it. Now we have var x equals b squared plus ab plus a squared over 3 minus, now if I get this, I have what? I have b plus a over 4 over 4. Now let me put this here, which is b over 4. And get part in the flow. So I have var x which is equals to b squared plus ab plus a squared over 3 minus, now b times b, I have b squared plus 2ab plus a squared over 4. This is this. I just expand it. Now, for us to proceed, we need to get the LCM, and the LCM of this is 12. So 3 in 12 is 4. 4 multiplies everything here. We have b squared plus ab plus a squared minus 4 in 12, which is 3, into brackets b squared plus 2ab plus a squared. Now let's use these figures to open up the brackets. We have 4b squared plus 4ab plus 4a squared. Now minus 3 multiplies all elements here. We have minus 3b squared minus 6ab minus 3a squared all over 12. Now we can collect the like terms. Here we have 4b squared minus 3b squared. We are left with what? B squared. Here we have 4ab minus 6ab. We are left with minus 2ab. And here we have 4a squared minus 3a squared. We are left with plus a squared over 12. So this expression can be rewritten as b minus a all squared over 12, which is the variance of a uniform distribution. Therefore, the mean is equals to b plus a over 2, and variance is equals to b minus a over 12. So in today's video, we proved the mean and variance of a uniform distribution. Thanks for watching, and I would love you guys to like this video, share and comment.